that. So, okay, it's also a way to activate your research. Okay, go ahead, Urkam.
Yeah, thank you. Thank you very much. Thank you for the invite. So it's a great pleasure to this opportunity to share my work with you. As you said, this is mostly my PhD work. So today I'm going to talk about mostly microcontinental terrains, also oceanic terrains, so maybe not, the title doesn't reflect maybe everything here, but it's mostly my PhD work and I'm finishing soon actually. So our other co-authors, Raspis Leves is also from University of Toronto. He's my supervisor. And Oğuz Göğüş and Gültekin Topuz, they are from Istanbul Technical University, from the Eurasia Institute of Earth Sciences. So let's get started. Yeah, before I go further, I just want to give you a general picture of what I'm going to talk about and what these terrains are, why we are interested in this topic. So as you can see in this map, so there are two shaded areas. One of them is gray shaded and the other one's red shaded areas. So gray shaded areas are basically orogenic baths and also active subduction zones around the Pacific Ocean. And the red shaded areas are the contemporary oceanic terrains. But as well as there are some of them have a crustal, continental origin. Let's say, for example, in Mediterranean region, there is one seamount. We know that there was a drilling program there. So we know that it has a continental crust. So it is, we don't know. Some of them are oceanic, some of them are not, but there are anomalously thick regions inside of the oceanic lithosphere. And they are carried together with the movement of the oceanic lithosphere to their final destinations, which is subduction zones. So when they reach the subduction zone, so because they are thick and buoyant, usually they collide and upgrade to the overriding plate and creating all this orogenic baths and also causing their crustal growth. Or sometimes they can subduct into the astronosphere too, depending on variety of factors. So in this study, in my PhD, I was focusing on this geodynamics of these terrains, and I'll show you my results soon. So, like in definition, terrains are alloctonous fault-bounded rocks with a different geologic history than that of adjacent rock units. So they are exotic terrains, they're coming from somewhere else with the movement of ocean lithosphere, and they're accreting their current location. So they could be, as I told you, it's a continental, such as microcontinents, island arcs, seamounts, and again, oceanic in origin, oceanic plateaus, seamounts, and seismic ridges. So today, in the first part of this talk, I will be focusing more microcontinents or continental terrains, and later I will be talking also oceanic terrains as well. So again, let's start with geology. So I love geology, and as well as I like this numerical modeling too, but this is the main concern of us. So what you see here is a mosaic of terrains. This is a map from Eastern Mediterranean region. And as you can see, all these different colors represent different terrains, and they all came together by the end of the process of the subduction zone. So for example, the Sakarya zone has like a Laurasian affinities, and this south of the Sakarya zone is a Gondwana affinities. But between the Sakarya and Anatolia Theory and the Kırşehir Massif, there's İzmir, Ankara, Erzincan suture zone, which is actually marked the graveyard of the Tethys Ocean. So Tethys Ocean subducted between these two units and bringing everything together and amalgamate in Eastern Mediterranean region. So where we are talking about all terrains, but here you see that there is Eratosthenes seamount, which is a modern terrain actually. This is where what I was talking about. So there was a drilling program happening here, and they know that there's this crust of this Eratosthenes seamount is continental, not oceanic. And it's been suggested that this Eratosthenes seamount choked the subduction along the Cyprus arc. So let's focus a little bit extensional tectonics, but these are not in general extensional tectonics, but mostly related to terrain geodynamics. So how could we create this microcontinent? So is one of the suggested thing is rifting. So you can take a piece of the continent from a bigger continental realm by rifting. So this is actually extensional tectonics. So what we know, actually, this is very well known, is that the post-collisional extension of this terrains or microcontinents or any other terrains too. So how does it work? So these terrains, microcontinents, they move to subduction zone, later stage. And after that, they collide and upgrade to the overriding plate. And after that new place, the new locations of this microcontinents or terrains are now in the backarc region. And with the slab retreat and slab rollback, so this part of the subduction boundary became a focus of extensional deformation. And having in the backarc, this terrains could undergo extensional deformation. So this might be related to slab retreat or gravitational collapse. By saying gravitational collapse, due to the collision related to shortening and thickening, so this crust cannot be supported by its own weight and start to collapse and creating normal flows or extensional tectonics. So this is very well-known process for post-collisional terrain extension or post-collisional terrain exhumation. But what we don't know, what is happening between this part and this part. So what is happening when this microcontinents or other terrains, when they are drifting towards the subduction zone. So are they going any under deformation or not? So this is the main concern of this talk. And also, I will be also a little bit talking about syncollisional terrain extension in the later stage of this talk. So let's go back to geology again. So here you see that there is a map of the Eastern Mediterranean region, again, from Western Alps to Eastern Anatolia. So as I said earlier, so we know that post-collisional terrain extension is a very well-known thing, but geology says otherwise. So for example, Western Alps, the Sesia zone in Western Alps in Italy. So it's supposed to be a ribbon-like microcontinent or continental block between Europe and Adria, and it was moving towards the Adria in this kind of cartoon, according to Rosenbaum and Lister. So, but the interesting thing is that, so if you look at this tectonometamorphic history of the Sesia, so we know that this crustal or mid-crustal or lower crustal rocks exhumed to the surface or subsurface levels 80 to 60 million years ago. So, okay, but what is the interesting thing here is that the collision is later. So it's 50 million years ago. So what does it mean? So it means that the Sesia zone underwent extensional deformation or exhumation related to extension happened prior to collision. So it doesn't fit this idea slab retreat and post-collisional extensional tectonics. And the second concrete example, evidence is coming from the Eastern Anatolia, this Akdağ region. It's the same history. So metamorphism starts 83 million years ago, and exhumation of these rocks of the Akdağ from lower crustal levels to surface, subsurface levels happens 81 million years ago. But again, we know very well that this collision along this Mirankos-Erzincan suture, closure of this suture is 50 million years ago. And again, this evidence says otherwise. So this extension happened prior to collision. So this is an interesting question. Well, how is it possible to create this kind of extension? So prior to collision, that's why we created this numerical modeling setup to investigate this intriguing question. So in this numerical model, so you see a subduction zone here, and there's one oceanic lithosphere subducting beneath another oceanic lithosphere. We set up this experiment like that because we knew that in Eastern Anatolia, there's an interoceanic subduction zone. And also this ocean lithosphere carries a microcontinent together with when it is moving towards this plate boundary. So we tested different size microcontinents to see is there any effect on the formation size. We start with 120 kilometer wide microcontinent and up to 600 kilometer wide. And also we tested different convergence velocities from 0 to 4 centimeter per year. So if it is 0 centimeter per year, it means that there is no imposed velocities affecting this system. So which means that maybe mid-ocean accretion, so it is pushing this lithosphere, ocean lithosphere towards the subduction zone. If it is 0 centimeter per year, it means that this velocity from right side is 0. But the only plate driving force in the system is the slab weight. So when the slab starts to sink, it pulls the upper continuation towards the subduction zone and creating almost 2 centimeter per year velocity. So on top of that, in the later experiments, we also apply from the right side of the model box, force up to 4 centimeter per year imposed convergence velocity. So at the end, we had 12 experiments here, and I'm going to show some of these results of these experiments. By the way, feel free to stop me if you want to ask something, and I'm okay with that too. So this is experiment 1 and 2 here, what you see. Let me explain some things related to this experiments. So in this smaller frame, you see the initial state of microcontinent. This is a 120 kilometer wide microcontinent initially, and this bigger frame on the left side shows that after 5.5 million years later. So this is the situation, and this is 7.1 million years later, which marks the slab break-off time. The 5.5 million year frame shows the beginning of collision. So, this initial state, beginning of collision, and after the collision, the slab break-off. So, to investigate that problem, so what kind of deformation styles were happening prior to the collision, we decided to track some rocks from lower crust levels and draw their pressure, temperature, time graphs on the right side. So this is actually going to give us about the test about deformation style. So maybe you can see that this is this extended state, we call it. So initially this microcontinent was 120 kilometer wide, but at the end, when it reaches the subduction zone, it is wider. So also you can tell this type of style of exhumation or extension history from the pressure temperature tab. For example, let's focus this pink rock here. It starts on the right side here. It's almost under 8 kilobar lithostatic pressure when this microcontinent starts to move, and there is a drop of the lithostatic pressure, which means that this microcontinent is extending. So it is thinning, and because of that, there's less rock on top of this point, and we see less pressure. So these solid lines show the first 5.5 million year. So as you can see, there is almost continuous pressure drop, which marks the actual extension. And there's other rocks, the green and purple here, you see there's a front part of the microcontinent and the back part show similar paths. So they show some extension first. When they start to collide, they bury again, you see that there is a clockwise rotation of these rocks. So the second part in this second experiment showed the similar setup, but this time microcontinent a little bit bigger, so it is 300 kilometer wide. So again, we see a similar trend in the pressure temperature path of these tracked rocks, but maybe you realize that the amount of exhumation is less compared to smaller microcontinents. So here, for example, it starts almost under 8 kilobar and exhumes around like a 5 kilobar-ish pressures. But here it is 7.5, maybe it's barely, maybe 5.5. So there is a drop in pressure, a decrease in pressure. So experiment 3 and 4, same. I'm not going to go into details, but again, here, I think most important thing to realize that the amount of exhumation is getting less and less when you increase the size of the microcontinent. And there is another thing to recognize in this models. Maybe you realize already, after the collision, you see the slab breakout happens not inside of the subducting oceanic lithosphere, but inside of the tip of the microcontinent, because we think it is weaker than oceanic lithosphere, it's more prone to break off than oceanic lithosphere. Again, the same things happening here too. You see the tip of the microcontinent is breaking up and going subduct. This is also interesting because you see that these rocks here, these are continental in origin. They are subducting very deep part of the asthenosphere. Okay, so then to understand what is happening, is there any relationship between these two experiments and size and the convergence velocities? We come up with this graphs. On the left side, you see individual pressure drops in this tracked rock packages. It's a little bit complicated to read. Let's focus on the right side of the figure. So we also calculate the beta factor, which is essentially the extension factor in these microcontinents. So if this beta factor is high, it means that we see more extension. And if beta factor is less, it means there's less extension. So we compare beta factor, extension factors versus a microcontinent width and also convergence velocities. So as you can see, there is a clear trend that there is, when we increase the size of the microcontinent, we see the extension less. So because beta factor is decreasing. And also another thing to recognize here is that when there is only slab pulleys acting as a driving force in the system, which is 0 centimeter per year, which is represented with the solid line, we see the highest extension rates. But if we apply impulse convergence velocity from right side of the box, or you can say this is the reach push, so we effectively decreasing the amount of extension. And when we increase the also more this impulse convergence velocity, it is getting less and less. Almost we are almost short of this extension process. Okay, let's go back to geology. Just a little bit more details about the Sestia and Eastern Anatolia zone. So the Sestia zone, so we know that I told you that for that this rocks of the mid-crustal level rocks exhume to the surface levels along this detachment fault here. And pay attention, this metamorphic grays, this metamorphic grays of this orange part of the Sestia zone, eclogitic mica schist, is higher than this blue one. So it means that this detachment faults, they, with the help of the detachment faults, this part of the Sestia exhume to the surface levels. So this map is from Do Avigat. So he is the one here that did field work and examined the rocks here using SC structures, mica schist, etc. So he's pretty confident that this worked periodic collision and is an extensional detachment fault. So also what we did, we compared one of our models against geological data using this pressure temperature graphs. So this purple and green colors represent one of our model, this is experiment 3. Our models are not as long as, million years. It is almost like a 10, 15 years, million years. That's why we cannot see the whole path of these rocks. But we can say this, they are comparable to the geologic data from these references. The paths are following similar trends. And if we focus to the Eastern Anatolia, this is actually this data and the map, all this, everything is coming from one of the co-authors, Gültekin and Topuz. He's a petrologist and field geologist. And he spent significant time in the Eastern Anatolia. and work on these rocks and dated them, etc. So this is from his work. So we know that this higher grade metamorphic rocks here in Akta region, which are late Cretaceous amphibolite-facies rocks, they exhume to the surface, subsurface levels along these detachment faults. So, and also we know that this the collision along the Izmir-Ankara-Erzincan suture was 50 million years ago. But these detachments were active prior that, from 80 to 70 million years ago. Also, there are other evidence here, the similar pattern, this higher grade metamorphic rocks exhumed to the surface levels. And again, there's probably a similar extension of deformation occurred on the western side of the Eastern Anatolia too. So what does it mean? So how is this possible? So we came up with this analogy here. We thought that it will be maybe easier to understand for everyone. So in our analogy, we call it subduction pulley. So what does it mean? So we juxtapose this tectonic units with a mechanical system here. So in this system, the subducting slab is represented by a weight in the mechanical analog. The trench is a pulley, and microcontinent is a weak continental lithosphere, is a dashpot. And this strong oceanic lithosphere represented by a string. The only discontinuity here is a dashpot because we think that this continental lithosphere is weaker. So with the movement of the, or sinking of the slab to the deeper part of the asthenosphere, or weight here, it pushed the upper continuation of the oceanic lithosphere. And this pulley plays a role that it is converting vertical to subvertical level tensile stress to horizontal orientation. And it is this strong oceanic lithosphere, which is represented by string, it is transmitting this tensile stress to continent, to microcontinent. But microcontinent is not as strong as oceanic lithosphere, and because of that, it undergoes extensional deformation. And how do we know that? Because there were some studies on oceanic lithosphere. They suggest if oceanic lithosphere is older than 10 million years, it should resist to tensile stress. But also we know that this continental lithosphere is more prone to deformation due to probably its crustal features compared to ocean lithosphere. So this study, all these results has been published in Nature Geosciences last May, if you want to have a look. So here the title of our work. So, okay, so for this part until now, so I focus on more continental terrains. But so what about oceanic ones? But before, I forgot that. So maybe I should show you first this movie. So this is one of our experiments, experiment 5, and we also juxtapose this cartoon or mechanical analog, this pulley analogy here, to show you how this pulley works. So let me play this animation first. So in this animation, see, this is from one of our experiments. The slabs start to sink and start to pull this upper continuation here. Pay attention to the size of the microcontinent. The more it moves and it starts to extend. So you see this extension in the microcontinent, and this happens prior to collision. And after that, the system continues and this microcontinent collides with the overriding plate. And after that, you see the breakoff is happening on the subducted tip of the microcontinent. And at the end, this model stops. Okay, yeah, so as I told you before, so what about oceanic plateaus or other parameters? It's okay that we had this microcontinents, and we want to also see is the same process also affecting ocean plateaus, or there are some other parameters we haven't tested yet. So maybe they're also responsible of also controlling these deformation patterns too. So to do so, we created we tested different parameters, such as, so in the previous experiments, we saw only ocean or interoceanic subduction setup. But now this time, we also tested ocean continent subduction zones. And also originally it was continental terrains. So we tested oceanic terrains as well. Again, the same terrain width, but this time we also tested 15-kilometer thick crustal thicknesses too. So originally these models were showing 30-kilometer thick terrain crust. So, sorry. Also, we tested different density difference between asthenosphere and mantle-lithosphere, which is effectively changing the slab pull, the magnitude of slab pull. You can consider that if it is higher, is the density difference, it means that maybe you can say the oceanic lithosphere is older. When it is older, it should be more dense and creating more slab pull. And we also decrease a little bit to see is there an effect on this pre-collisional extensional. And again, we tested different convergence rates up to 4 centimeters per year. All these parameters yield 288 experiments in total. So originally we had 12 experiments, and now we continue this research, and now we have 288 experiments. So this is the setup. So the upper part is exactly the same one on the previous models, but here you can see that there is a continental overriding plate, in addition to oceanic overriding plate. And also again, this 15-kilometer thick crust, and also type of the oceanic, the crust is also oceanic as well. So this is a summary of our experiments. So what does it mean? Here, these blue colors represent extensional deformation. So it's a kind of average of this deformation styles in this not microcontinents. Now everything is like every type of terrains, continental and oceanic. So blue represents in basically extensional cases, and yellow and red represents shortening or burial cases. So what does it mean? So in this model, you see the 288 bugs. So this, maybe I should focus one by one. It's hard to read figure too. So for example, in A, so we are showing here only continental terrains similar to the first models I've shown you in ocean-ocean subduction zone, which is interoceanic subduction zone. The first set of the models I've shown you before, they were only in this box, this 12 models. Now we expand everything, every parameters, and we have 288. So the column here represents 30-kilometer thick crust experiments, and this is 15-kilometer thick crust. And here the same thing for oceanic terrains in ocean-ocean subduction zone. And if you go to bottom part of the figure, you see the continental terrain in ocean continent subduction zone. And again, oceanic terrain in ocean continent subduction zone. So what you can see, there is a clear pattern here. So when the crust is 30-kilometer thick in these microcontinents, we see mostly extension. So either ocean continent subduction or ocean-ocean subduction, doesn't matter, or oceanic terrain versus continental terrain. If the crust is thick, so we almost see in every case, except this gray ones are not significant deformation, mostly extension. So it tells us that this crust thickness, or the amount of the crust, is controlling the bulk strength of the terrains actually. Because if we test 15-kilometer thick crust terrains, let's say here and here, we start to see some shortening cases or contractional or burial cases here and here. So also another thing to recognize here, that this interoceanic subduction zones are creating more extensional cases versus ocean continent subduction zones. And this is due to probably the size of the overriding, thickness of the overriding plate, because continental overriding plate is thicker, is creating more friction in the subduction zone probably, and effectively reducing the slab pull force. So as I told you that we also focus a little bit syncollisional extensional cases too, but as you can see, there is no clear patterns here. So because this is due to, we see so many different geodynamic events during the collision, because we see sometimes break off, continuous subduction, etc. And that's why it's not easy to find a pattern in this during the collision. But we can say that if microcontinent or oceanic plateau or oceanic terrain versus continental terrain, if they're smaller, like 120 kilometer, so we don't see much syncollisional extension. It's mostly no extensional cases. This is due to this, I think, if the microcontinent or oceanic terrains are too small, so it just, in the collision zone, it cannot create any extension. It's just toasted between these two overriding and subducting plates. So this is a kind of summary figure. Again, I'm comparing here all these experiment results. Again, it is similar to this figure here. We are using the similar placement of the models. Here on the top part, we see interoceanic terrains, interoceanic subduction zone, at the bottom continental subduction zones. But now we choose only a few parameters to show here. Only, for example, you see 450 kilometer wide terrains, continental and oceanic. And also we are comparing 15 kilometer thick crust cases to 30 kilometer thick crust. And also we are showing here this different density difference between mantle-lithosphere and asthenosphere. So let's focus on the first part here. So as you can see, if the crust is 30 kilometer thick, we see significant extension prior to collision. So it doesn't matter what the density difference between slab and the asthenosphere is, we see always a significant extension. As you can see, there's the slab, the magnitude of slab is not affecting too much. So we see mostly similar extensional magnitude. But when it comes to the 15 kilometer thick crust, again, we see some extension, but not as much as what we see in this 30 kilometer thick crust cases. So if we look at the oceanic terrains, they show similar results. Again, when there is when the crust of the oceanic terrain or oceanic plateau is, let's say, 15 kilometer thick, we don't see any significant change here, actually. Even maybe can tell maybe slight shortening in the mantle-lithosphere, but we don't see a clear extension here. But again, when we increase this, the thickness of the plateau crust, so we see again significant extension. So this supports this idea that this crust is controlling the formation style, the thickness of the crust. So for the continental overriding plate, we see same. As I told you before, we see more shortening cases in continental overriding plate. Let's go back to this figure. You see this red and yellow cases. So they miss that shortening. And here you see shortening case here. You can maybe consider the shortening too, but not any significant extension here. Only maybe in one case when the slab pull is, the magnitude of slab pull is high. And again, if we increase the crustal thickness, we see immediately a change in the extension magnitudes. So same thing for oceanic terrains. And again, shortening to no significant change, maybe a little bit shortening too, but oceanic terrains mostly show more shortening cases compared to continental terrains. And again, when we increase the crustal thickness, we start to see more extensional cases. So let's compare this individual model sets. So it will be maybe easier to understand. So in this model, we pick some of the terrains to compare. These are all continental overriding plate models. And we are comparing here oceanic terrains having 120 kilometer wide versus 300 kilometer wide. So they have 15 kilometer thick terrain cross in both cases. The only difference is the width of the oceanic terrain. This is the initial state at the beginning of the experiments. And this B and G show the pre-collision state. So it starts to collide with the overriding plate. So as you can see that we have not much extensional deformation here because this crust is 15 kilometer thick, but still we see something. And also it's also important to recognize here the effect of the impulse velocity, impulse convergence velocity. If we have 4 centimeter per year impulse convergence velocity, we don't see much extension. Actually, it's effectively shutting off the extension that originated from the subducting slab. But for example, if we check the 0 centimeter per year model, so it means that slab pull is the only plate driver force in the system, even if it is the terrain cross is 15 kilometer thick, so we see some extension. And compared to 300 kilometer wide, we see some similar results. There's not much difference between these two. Either small terrain or bigger terrain, the results are comparable. But what about post-collisional state? So we also check what is happening after the collision. And firstly, we focus on pre-collisional and syn-collisional cases, but we want to see what is happening because the results are interesting. So for example, for post-collisional state, for the 4 centimeter per year model, see that this oceanic terrain or oceanic plateau, or maybe you can say this is a seamount because it's not so big, 120 kilometer wide. It doesn't leave any trace on the surface. It subducts completely to the atmosphere without leaving any trace, no significant deformation or anything that's so. And subduction is also continuous, doesn't stop subduction. We don't see any break of anything. But when we reduce the impulse convergence velocity to 2 centimeter per year, in addition to the slab pull, again, we don't see much difference here, but maybe some crustal rocks start to accrete, but not on the surface. So this is also not a good case. But if we don't apply any impulse convergence velocity, which is bridge push, you can say, we start to see some accretion, even if it is a tiny bit terrain, like 120 kilometer wide, we start to see some accretion in the overriding plate. It's minor, but again, subduction is continuous. There is no choking of the subduction process or no breakover, etc. So for the 300 kilometer wide one, we see similar results, but more accretion in these models. For example, in this one, we can effectively subduct a 300 kilometer wide oceanic plateau, but without leaving much trace on the surface. Just a little bit maybe accreted rocks here. The rest are the crust rocks of the plateau. So when we decrease the convergence velocity to 2 centimeter, again, we start to see more accretion here. But if there is only one acting force in the system, such as slab pull, we see much more extension, accretion cases here. And the slab cannot, the slab cannot pull this part anymore because this is buoyant and doesn't want to subduct. And we see the slab stalling here. Probably is going to break off in the later stage of this models. Okay, what about 30 kilometer thick crust? The difference between previous and this model sets are the crustal thickness. So in these models, we have 30-kilometer thick crust in this oceanic terrains, let's say seamount or oceanic plateau. Again, we see similar results when there's we see obviously more extension here compared to 15-kilometer crust. In both cases, 300 kilometer wide or 120 kilometer wide. And again, we see the trend of decreasing extension magnitudes when we increase the impulse velocity. But the intervening part is the post-collisional state. For example, in this 4 centimeter per year models, yeah, we start to see some minor crustal accretion, but also we see some delamination here. As you can see, this crustal part is mostly delaminated from the subducting oceanic terrain and kind of placing beneath the continental overriding plate. If you decrease the impulse velocity, we start to see some accretion, and also subduction is probably continuous here too. But compared to previous ones, for example, we were seeing a much clearer continuous subduction process, but here, not so well. And for example, when we decrease the impulse velocity to 0 centimeter per year, we see this complete break-off, which was not happening in the first cases. So even a tiny bit terrain, like let's say seamount size 120 kilometer wide terrain, could stop subduction and could cause a break-off process when only slab pull is acting force in the system. For the 300 kilometer wide terrain, we see similar thing. So if the impulse velocity is high, we see some subduction of this oceanic terrain, but again, still we have some significant accretion here too. I mean, compared to previous model here, if the crustal thickness 15 kilometer, we don't see much accretion, but if it is 30 kilometer thick, we see significant amount of the crustal accretion here. And again, when we decrease the impulse convergence velocity, we start in more accretion, and again, slab break-off cases. So what about intraoceanic subductions on these two sets for continental overriding plate? In this set, we have oceanic overriding plate. So results in the first part, similar. I'm not gonna talk again this part, pre-collisional state. We know that there's extension in both cases, but this post-collisional state is again integrating because of the changes in the subduction dynamics. Again, 4 centimeter per year model, similar to previous one, we see some delamination of or scrapping of the plateau crust and placement beneath the overriding plate. But the intervening case start to come when we decrease the impulse velocity. See, now it is 2 centimeter per year model. And so with the collision of this, or maybe you can say subduction or collision of the this tiny bit oceanic terrain triggers an ablative subduction. So it's a double-sided subduction because both sides of the system here is oceanic lithosphere. So it means that this overriding plate could subduct too. So when this oceanic terrain or seamount collides with the overriding plate, it bends the tip of the oceanic lithosphere a little bit to down. And then after that, it reaches to the other part of the subducting, and they start to subduct together, almost symmetrical. And this is how you can trigger an ablative subduction with a collision of terrain, actually. It's an interesting result of our models. And now we are decreasing the impulse convergence velocity. And again, this is interesting too. So now instead of ablative subduction, we see a subduction polarity reversal. And this microcontinent collides with the overriding plate, but there is no impulse convergence velocity. It's not easy to subduct this one because it wants to stay on the surface, right? It's due to its buoyancy. So it holds to this part up, but not the overriding plate part. Because of this bending, now with the collision, we see the polarity switch and the overriding plate starts to subduct and changes the polarity of the subduction. But what about 300-kilometer wide model? So again, we have similar results here, like so many accretion, but also crustal accretion, but also the mantle lithosphere of this oceanic terrain mostly subducts. And 2 centimeter per year model. In contrast to the 120-kilometer wide one, we don't see any ablative subduction here. So it means that the size of the plateau is also important that controlling this ablative subduction or not. So why we don't see here ablative subduction? So this is due to this oceanic terrain or plateau is wide enough and plays a role similar to a bumper. Just these two plates could not reach each other, and if they cannot touch each other, so they cannot create an ablative subduction. So it is kind of preventing and playing a role of like a similar to a bumper between these two plates. But again, for the 0 centimeter per year model, when we decrease the impulse convergence velocity, we see similar result here. We see a polarity reversal. Okay, let's go back to geology. Maybe it's boring to see all these numerical models. I know that maybe geology is more fun. So this is a paleogeographic construction of the Tethys Ocean in the Eastern Mediterranean. So this map is from Okai et al. 2018 paper. According to their work, there was an oceanic plateau called Nilüfer Oceanic Plateau, and it was drifting to the north to Laurasia continental margin in the late Triassic. So the size of the plateau is almost 1,000 kilometer long and maybe 150 kilometer wide. So this is the current map of this region. So this is from Turkey. Actually, I'm from Turkey originally. So you see this is outcrops of the accreted Nilüfer Oceanic Plateau along this Laurasia margin of the suture zone. So what we know that, so according to their later work, they suggest that this Nilüfer Oceanic Plateau collides and accretes partly to the overriding plate, but it didn't stop the subduction zone process. So Arlokai and his team also, they're really good petrologists and field geologists. They suggest that the subduction was continuous here, but still we see evidence for the accretion of the oceanic plateau. So this is a good example to compare my models to this geologic example. To do so, we compare these cross sections of one of our models to tectonic evolution of this Laurasia and the Nilüfer Oceanic Plateau margin. These F and G frames are coming from Okai et al.'s 2020 paper. According to them, so this Nilüfer Plateau was colliding with Laurasia margin and partly accreting, but without stopping this subduction zone process. So, and also interestingly, there's their paper back in 2000, they published, and there was another paper. They're also saying in the field evidence, they see layer parallel extension prior the collision. I forgot the other reference, but there is another paper. They did a field work there and along the northern part of the Turkey. So they see similar woodinized structures, layer parallel, strong layer parallel extension, etc. So it fits our pre-collisional extension idea, but now is in the plateau, actually, in the oceanic plateau. So this model, I'm comparing one of this 120 kilometer wide model here. So we calculate there's extension here a little bit, and after that, this plateau starts to collide with the overriding plate. This is their interpretation. This is our model. They look so similar, actually. And then after that, we see scrapping of the plateau crust in our models. And at the end, this plateau continue to subduct without stopping the subduction zone, is what they suggest actually in their interpretation. So geology versus model, they fit. So at least for now. So this is the summary of this study. So this is just a general comparison of these parameters. So what we can say that if we increase crustal thickness and the terrain width, and also having a continental overriding plate promotes terrain aggression, but the impulse convergence velocity, lower impulse convergence velocity, and the dense difference between mantle-lithosphere and sublithospheric mantle or asthenosphere is acting against it. So for the pre-collisional extension, we know that crustal thickness and higher density difference between mantle-lithosphere and asthenosphere promotes pre-collisional extension, as well as having an interoceanic setup. But on the other hand, if we have a lower width and a lower convergence rate, so it is also promoting pre-collisional extension. So all this results of this study, this 288 models and much more things in this paper that we published just 2 weeks ago. So thank you very much. So if you have questions, comments, I'm happy to answer. Is it too fast or is it on time? I don't know.
Actually, yeah, it's pretty good. Okay, thank you very much for the great talk. And now it's time for questions from our participants. Okay, now we do have one question from the chat. I'm going to read the question that we have. Okay, the RKUT from Institute of Technology is asking, can we estimate the effects of addition of fluid at the metal wedge that might constrain the rate of extremation of the microcontinents and the underlying mantle as well? Okay, that's a good question, but we didn't test any fluid-related effects actually. In our code, we cannot incorporate these fluid effects. Sorry that I cannot answer this one. Yeah, unfortunately, not this model. I'm using a code called SOPAD. It's a little bit old code. But the thing is that I'm going to start using another code. It has also 3D capabilities called Aspect. Maybe you're all aware of that. So I think we are going to test that parameters too. There's so much things to test. So actually, just with these parameters, we had 288 models. But yeah, this is in our bucket list actually. So the second question, can this model together change in pattern channel flow? Yeah, so again, we didn't look for channel flow or subduction channel flow, that kind of stuff. Okay, next question, Train's asking that how about deformation overlying? Sure. Also affect the overlying plate. Yeah, again, so we didn't focus on the overriding plate side of the system. We were more focusing on the subducting plate and terrain or drifting terrains. So we didn't investigate that part of the subduction zone. So yeah, you're right. So it is important too. Maybe in the future, so I will be focusing, maybe calculating the overriding plate thickness or topography, that kind of stuff. But so far, no, we haven't looked at those actually. Okay, so Trina's asking about 3D model is a more consistent reality. Well, what about difficulties in using 3D modeling? As you mentioned that you're about to use 3D models. Yeah, so unfortunately, we haven't started 3D models yet. So this is the last part of my PhD. Actually, I'm supposed to start this 3D models, but due to this coronavirus, so we couldn't start those. But hopefully, we will be also investigating in this 3D geometry too, because it's important. It could maybe increase the, for example, pre-collisional extension in 3D. So if this laterally if the subducting slab is forcing this, or maybe pulling these terrains, could create more pre-collisional extension. On the other hand, it could also limit the extension too. So it will be interesting to see actually this too. And also, you're asking what about difficulties in 3D modeling? It is the time actually. So you need more computational power. Sometimes the code I'm using is, I mean, this 2D models usually take 10 hours to finish. But for example, these other models, even if you have supercomputers, sometimes it takes weeks to calculate and get the results. So 2D versus 3D, this is the thing. It is fast. You can get your results immediately in 2D, and you can change the parameters and test more models and to see, like, let's say 288 models. It will be hard to do this in everything in 3D actually. 3D should be, I think, maybe you should be thinking some specific cases and test this cases more, maybe not like a broad testing parameters, but maybe more focused ones. But thankfully, this now we have supercomputers, and things will be much faster and faster. I will say this is the difficulty of the 3D modeling. And also another thing is that, yeah, so in 3D you have more parameters to incorporate, right? So what about the length of the let's say microcontinent, or the ocean plateau, or overriding plate geometry, or different geometries? There are so many things to test.
Okay. Do we have more questions from the participants? Okay, I have a quick question. Maybe it's a little while. As you are showing this, I'm thinking of naively that it will change the surface topography. So I'm thinking about that. Will this, let's say, in both cases that you have been modeled, that do you think that it will affect with the surface weathering rate?
Surface weathering rate on the overriding plate, or
overall the Earth surface? Because as geologists, that
actually, because it could. So because in these models there is no erosion or sedimentation, but it would actually. So my supervisor had this models in the past. I think he used the similar things for New Zealand. There's continental collision there. So, but not for this model. It will be also interesting to see that effect too, because so you're thinking maybe the subduction zone will affected by this weathering process, right? Is this what you mean?
Actually, I was not thinking about that. I was thinking about something else that we care about. So for weathering, I think there are two things that overall that I think is very interesting to look for. One is, of course, it affect the global climate, because weathering is one way that will affect.
You are seeing interesting things, because this is kind of one of our future plans to see or incorporate climate models with this numerical geodynamic models, and to see in this in general how could they affect in a broader scale actually. So it will be interesting to combine climate models maybe with this geodynamic models. But yeah, so I don't know if I can do it in the short term, but in the long term, yeah, this is one of my goals actually.
Yeah. Another thing that also I have been thinking of is that for geologists, that the paleo samples, I mean the old geology samples being preserved, of course they are being selective. The farther we went back, trace back, the fewer samples that we have. So it is inevitable that they are selective and likely biased. I think through the geodynamic process, I think overall the community could provide us with some ideas of this, how this process could be, and what are we really sampling it. So what the community now could do in petrology is what we are seeing is that we're getting the like igneous metamorphic samples preserved on the one hand, and on the other hand, people look for some sedimentary samples, especially related with a glacial related process to try to estimate the average composition. For example, the average composition crust that a lot of people are interested. So I think for your process, the work that you presented actually showed, I think it's quite insightful for me to see that some parts that are more likely to be preserved than the others, since you let them assume that rather than being abducted and completely, let's say.
I should also say maybe the one thing I forgot to say. So again, in this modus, we don't have erosion because they're a short-term modus, but it will effectively actually increase the exhumation rates, having an erosion in this modus. So we are getting this much more, we will be getting much more exhumation or pressure drop if we will incorporate also erosion in this modus too. So maybe that's why we should keep testing more modus and more modus, but there's no end. So this is really like a 288. I don't know how much time I spent on this modus, maybe years during my PhD, but as you say, there's like a weathering, erosion, sedimentation, and now after you start to test these parameters and you're going to test, okay, maybe I should change the erosion rate from that one, that to adding one parameter doubles everything. It's a kind of exponential growth of this modus, and we don't have that much computational power or maybe time or even plotting all this data and seeing the results. It is time consuming. So maybe we should be incorporating machine learning algorithms, this modus, and instead of testing everything, adding parameters, let the machine do. So in our group, actually, there is one person doing this kind of work, but not maybe what I've shown you today. But I think machine learning is the feature of geodynamic modeling. I don't know, we'll see.
Okay, thank you for pointing it out. Because in my own research group that we are applying machine learning geology, and at least now it works pretty well for several thermodynamic exercises. Yeah, another way is that machine learning that could dramatically improve our computation. I think it has already in first calculations where people used to model several items, and now people could model with the same computational power, people could model millions of atoms, and therefore making trace element possible in terms of trace element partitioning at the Earth's extreme condition possible using the first-person calculations. I bet that is similar in the geodynamics. Another thing that I happen to talk with other people in the, not in earth science, but in computer sciences and the physics community, for example, quantum computing, that is also on the way. People don't know that how fast it will become effective, but it could be specialized in certain tasks. It is not general computers, but specialized in certain tasks could be extremely effective. Actually, some industries are trying to use it now because I have been looking at some of my other colleagues in the computer science and data science that they're trying to write proposals for certain competitions, for example, by BMW, and they are trying to use quantum computing for certain industry exercises, but only for a very specific task. So to me, I think some of the earth science question that is computation intensive might also serve for that very similar purpose. That could dramatically making the very limited resources, computational resources we are available by dramatically expanding it, and therefore could make a lot of things that are realistic. And of course, machine learning helped to accelerate that process. So for what we have been talking about today, maybe in the future is likely to make them all realize.
So the good thing is that so now we have all these tools, new tools actually. So they the geologists didn't have in the past, and to imagine what was happening, maybe drawing some cartoons. Now we can test these ideas if they work in reality using this rules of the physics or not. So these are really good tools. But I consider myself still a geologist using numerical modeling as a tool. So machine learning too, maybe in the future, or anything, or maybe fieldwork. So everything is a tool for me to understand the geology of the Earth. So Yeah, every tool is welcome if they're going to be useful and help us to understand the Earth's history better.
Yes. Okay, great. Erkan, thank you very much for talking.
Yeah. Thanks for the invite. It was a great pleasure to share my work with you. So hopefully after this coronavirus, everything over, we will be seeing each other in conferences. So
yeah. We hope that everything will return to normal, at least return to pre-2020
yes,
status.
hopefully.
Okay. Erkan, thank you very much for the talk, and thanks everybody for your participation. And have a good day, have a good evening, have a good afternoon, everyone. Bye-bye.
Thank you.